I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students and for this time we have to study your creation. Just ask you to bless this class, Lord. In your name I pray. Amen. Before I forget, let me take attendance. So, where'd that go? Where is it? Yes, here. I wouldn't want to lose any points to not taking attendance. It does help when you talk about asking about taking attendance before class actually starts. It's always an aid to me remembering. So you'll find a way to put a date on there. Good luck. All right. Okay, so the daily quiz problems. Problem number 1. First of all, get rid of all these glasses. I finally found my glasses again. It's exciting. They were in Dr. Skambordis' office the whole time. I was talking to him this morning, and I looked down, and I'm like, are those your glasses? He's like, no, I just found them in here a couple weeks ago. I don't know whose they were, so I just left them there. I was like, those are mine. And I've looked everywhere for those, but I'm happy, very happy to find them in his office because it makes me feel better about the fact I couldn't find them in my office or at home. After extensive searching, I feel like my searching algorithm's not wrong. It's just, Anyway, all right, so find the potential function little f such that the gradient of little f is equal to big F, if possible. So here's our vector field, and here is our alleged answer. Let us check. Moment of truth. What happens when we take the gradient of xy squared plus y e to the z? What do we get? I get 2xy. I get e to the z plus 2xy. And I get y e to the z. I think. Did I do that wrong?
Yes. Yeah. Just when you took it as it goes, yx squared.
Oh, that should just be, if I could do math, differentiate that with respect to x, we get y squared. So the error is not with the solution, it is with the error checker. Always a problem.
I think in the middle term, it was raised to the z. Oh wait, never mind. Sorry, I was looking wrong.
Aha, an error in the error checker's checker as well. Let me draw a line. There we go. Now you can see where problem 1 starts and problem 2. Okay, so yay. Indeed, this vector field is conservative. In fact, there you go. We just found its potential function. How did the students find that? What method did they use?
Just thought about what you would have to, like what function you would need to take the
So what you're saying is you made an educated guess.
OS.
Yeah, and that's fine. That is a method, right? So. Now, of course, if you started to doubt whether or not you could do this, you could calculate the curl. If the curl worked out to be non-zero, then there would be proof positive it's not conservative, right? Because we have that theorem on a simply connected region, at least. There are these malevolent examples where the curl is everywhere 0, except at like 1 point, and that spoils that theorem. Like the vortex is one of those, the vector field, the vortex vector field. All right, anyway. So here you're asked to calculate a line integral in the dx dy dz notation. At the start, this problem was ambiguous because I forgot to put an ellipse in the xy plane. Without knowing it's in the xy plane, this problem does not make sense. But if it's in the xy plane, then here you go, a parameterization of the curve that clearly the students thought of. And no, I'm just kidding. I do try to help you guys out. Although, ooh, boo, boo I say. No, 0 less than or equal to t less than or equal to 2 pi is what you need to get the full ellipse, right? Because like this would be t equals to 0. So you guys up here is t equals to pi over 2 in this setup. So like, restricting the domain just to that would just pick off that one little snippet of the ellipse, which is not what we want. So anyway, aye, really? Ah, is that what happens? Oh, so you doubted me. So they're checking that my parameterization actually makes sense, which is good. I mean, it's good to be critical. But in fact, it does make sense. Woo. So we're going to erase that. And I'm also going to erase the offending, well, all of this. So, sorry, it's not quite right. And the reason it's not quite right is you're not, you got to go back to the definition of line integral. How do we do it? So we have dx is minus 3 sine t dt. dy is 2, my apologies in advance if you already wrote what was right and I'm just messing it up now. We'll find out in a minute. dz equals to 0. I sensed an error, so I erase. I haven't critically thought about that being an error or not. There's your differentials. So to calculate the, let me call this thing Pac-Man. So Pac-Man is the integral from 0 to 2 pi, and then I have to take my expression and evaluate. Now you might have the right, I mean you had part of the right thing, but I just don't think that what was missing was important. So yeah, that is the sine of 3 times the cosine of t. Okay, and that's kind of scary, but it becomes less scary if you multiply it by dx. What's the dx? Well, the dx is minus 3 sine t dt, and that's ever so very important. I'll put a dt here, fine. And then the next term, what's z? Oh, awesome, 0. And then cosine, what's y? 2 sine t, actually doesn't really matter, right? What's the dy? 2 cosine t dt, and then another 0, right? Because dz is 0. So look at this. This is 0. That is 0. So you can neglect the last 2 terms in the line integral intuitively. As soon as you look at this problem, you should have in mind, well, this isn't that bad. I really just have to calculate the first term. The other 2 are clearly 0 just from looking at the problem. Now, what you guys were missing and what I erased was this very important term which comes from the dx, all right? Without that, yes, the integral is very scary. In fact, I don't think I can do it. But with this, we make a what? U substitution. I think we can let u equals to, 3 cosine t. So du is minus 3 sine t dt. Oh, that's kind of funny. So what's u of 0? It's 3. What's u of 2 pi? 3, yeah? Because 3 times cosine of 2 pi is still 3. So when you make the u substitution here, we find ourselves with a very unusual kind of integral. Integral from 3 to 3. Yeah. It's the sine of u du. That's 0. Now I talked to you, you guys might have been thinking about whether or not this is a conservative vector field. And I wonder myself now, is this a conservative vector field? If we could have seen that this was a conservative vector field, we could have avoided this calculation because the integral of a conservative vector field around a loop is 0, right? Is this vector field conservative? What vector field am I talking about anyway? There's no vector field here, right? What vector field am I talking about? I am talking about f equal to sine x, z cosine y, and sine y. So let's use the last group's method. Let's try some educated guessing. F equals to what? Yeah, you definitely need a minus cosine x. That's, and then what? Plus z sine y. Aha! See, if you had not let your belligerent instructor talk you into doing an explicit calculation, if you had been, you know, embracing that you should be looking for conservative vector fields to shortcut your work, this would have been a far more clever solution, right? You look at the problem, you say, aha, the vector field sine x, z cosine y, sine y, that has potential function f, right? So when I look at the integral around the ellipse of f dot dr, that's really just the integral of the gradient of f around a loop, right? And that's 0. Pick any point you like on the ellipse. We can use the fundamental theorem of calculus for line integrals to get that we have f of p minus f of p, which is 0. You know? So it makes sense that the answer worked out to 0 also. Any questions? I know it's been a while since we've talked about conservative vector fields at this point, but it's important to remember that's kind of a big part of the test, right? That's the, you know, first chapter in this story we're telling. And then this problem here, oh, I should not have left this green marker up here. I'm going to have to retrace your steps. This is t, and t plus 1. This is for 0 less than or equal to t less than or equal to 1, because I told you so. Does that work? Plug in 0, what do I get? So sorry. No. To quote my community college professor, this dog will not hunt. Let's see here. So yes, in fact, we need to add 1 to both of these to make the formula work. I mean, the second one's fine. But then if you plug in 0, you get 1, 1, right? If we plug in 1, we get 2, 2. So there's the parameterization of that line segment right there. So unfortunately, as you know, the saying, garbage in, garbage out. And so unfortunately, this all falls down. This, by the way, I don't think is available here. Can you tell me proof positive that this vector field's not conservative? How would you check it? If we have a 2D field, PQ, then f equals to the gradient of f if and only if qx equal to py, actually. This is the two-dimensional conservative check. That amounts to checking that the curl of the vector field p comma q comma 0 is a trivial curl. Because if you have p comma q comma 0, the only non-trivial component to the curl is the third component, and the third component to the curl is qx minus py. So if qx is equal to py, that stands to reason, I mean, this is equivalent to the curl of the vector field p comma q comma 0 being 0, which from our theorem is conservative provided that we're checking that on a simply connected region. In this case, the whole plane is a simply connected region, which we can think about using. So is qx equal to py here? I don't think it is. See, this is my q. The partial derivative with respect to x is 2e to the 2x. This is my p. What's the partial derivative with respect to y? It's this again. So this is not equal to twice that. This is not a conservative vector field. So unfortunately, this way of thinking is forbidden because there does not exist a potential function. I wish there was. Conservative vector fields are ever so nice, but not always a possibility. So unfortunately, I have to erase this, but it was a good try. It looks like you guys are doing the right thing based on the wrong foundation, so I guess that's good. Although I'm a little bit concerned because what I just erased, it looked to me like you had the velocity vector wasn't 1, 1. Your velocity vector should have been 1, 1. dr dt should have been 1, 1, even with your formula.
It was.
Oh, okay. Well, I maybe I looked at it wrong. Okay, so this is, we're supposed to look at f of t plus 1, comma, t plus 1, dotted with dr dt. What's dr dt here? It's 1, 1. So, okay, that's actually the integral from 0 to 1 of parentheses e to the y minus x. What's y minus x? 0. Ah, good. And then e to the what? 2t plus 2? Okay, great. And then we're supposed to take the dot product of that with 1, 1, integrate over dt. So integral from 0 to 1 of 1 plus e to the 2t plus 2, right? So the 1, it integrates to 1. And so we're going to get here, what we get is 1 plus 1/2 e to the 2t plus 2 evaluated from 0 to 1, because the antiderivative of 2e to the 2t plus 2 is 1/2 e to the 2t plus 2. And so what's that give me? 1 plus 1/2 of e squared. I can't do math. E to the 4th, right? 1/2 of e to the 4th minus 1/2 of, now e squared, yeah. So there you go. It ain't pretty, but I think it's right. Okay. So, is this a particularly elegant problem? Maybe not. But this is a pretty standard test question, the one I just looked at here. If I assign that question on your test, I can pretty clearly see whether or not you have, done your due diligence and know how to calculate a line integral from first principles, right? Now, I do like to test about conservative vector fields, but sometimes it's not about conservative vector fields. Sometimes it's just about calculating the line integral. Significance here would be that this is the work done, right? This is the work done by the vector field e to the y minus x, comma e to the 2x along the line segment from 1, 1 to 2, 2. There you go. That's the work done. Yeah? No? Okay. All right, so here I gave you some weird facts about integrals around various loops for a vector field. It's 2 around C1. The integral around C2 is 7, poorly drawn 7. And then I tell you that the curl is 0 on R. Now R, I could, the R I'm talking about is this R here. So on a test, I try to shade that in with some, shading, but shading is a little bit shady on these boards. Let's see here. So, not sure this is, I would like to say it lived a good life, but I feel like it never really got used. It's a metaphor for so many things around here. Well, anyway, I don't know. Got a lot of expensive equipment that never seems to get used. But anyway, I digress. I'm not sure even what I'm talking about. It just seemed like a good thing to say. All right, so the point is that the integral, this is Stokes theorem with holes, right? So the rule is that if you have a holy surface, like this one, that you count the counterclockwise outer edge as positively oriented, and the counterclockwise outer edge is positively oriented. Clockwise oriented holes are positively oriented. So as my picture goes, C3 is got the correct orientation. C2 has got the correct orientation because it's a clockwise oriented interior hole, interior edge. But C1 is counterclockwise. So that's opposite what it's supposed to be to get the positive orientation from R, which again, as they pointed out, we can think about our little people walking along the edge. If it's positively oriented, the surface should be on their left. Anyway, since this is 0, we have that the integral around the boundary of R must be 0. But the integral around the boundary of R has 3 pieces. It's got C3, it's got C2, and it's got minus C1. See, they pulled the minus out of the curve using the oriented property of the line integral, which is good. Then the thing I asked Jim to find was the integral around C3, so they solved for that, like so. And that gave us minus the integral of C2 plus the integral of C1, which was minus 7 plus 2, which gave us minus 5. Yay! Does that seem like a hard problem? Then why do 80% of the students that I ask this question to on the test get it wrong? But you're going to change that statistic, right? If I was to ask this question, you'll prove those other previous students to be dummies, right? Put them in their place. So tell them, you should have got this problem right, you dummies. And then we'll go on to a brave new future where students get this problem right. It'd be amazing. I love it. Yes?
We just write down -7 plus 2 plus -5.
Can you just write down the answer? I mean, you can, but if you're wrong, then I take off all of the points. See, if you write down some work and I can see what the error of your ways was, and I can see that you're using Stokes' theorem, then it gives me something to work with when you're not exactly right. Now, I oftentimes sell this thing I just did as a deformation theorem. Another way you can look at this is that the integral around the outer loop, when you have a curl between the interior and exterior loop, when the curl is 0 between those two, then all of the line integral, the circulation around the outer loop is coming from circulations around the inner loop. And so like C1 is in the same way as C3, so it counts towards C3. But C2 is opposite C3, so it counts against that. So the fact that the C1 was 2 and the C1 was 2 and the C2 was 7 immediately tells me that 2 minus 7 is minus 5 is the integral around the outside loop. That's using the idea of the deformation theorem, which is mathematically equivalent to the argument I just showed you with Stokes' theorem. So, but anyway. Obviously, that's easier to calculate. Oh, man. I thought this one was going to be done. Curses. Ah. So much suffering. Why? Why did I ask you guys to do this one? I know it's because it might be on the test. That's right. I know it's true. It's true. It's all true. It's real. It's a problem that exists and we should be able to solve. And it's a pain. All right. I think for the sake of everyone involved, I should erase this board and start from scratch so we can make sure we understand what I'm doing. I mean, there are some good things on that board, don't get me wrong, but I want to make sure that I can clearly communicate to everyone all of the steps, all right? Over here, for the divergence theorem, the integral of the divergence over the volume, I think, is correct, but we were not successful in calculating the surface like this side. The direct calculation of this is not this. So maybe half of that's right. I don't know. All right, well, get to work here. I'll start with problem 5. So guys, I don't know if you read your email or whatever, but I moved the math battle to Thursday so that more people will be here. And also, so that we have more time. That's good, right? It's better that way. All right, so the problem is verify Stokes' theorem, which says what? It says that the integral over the boundary of a surface of f dot dr, the line integral, that is equal to the surface integral over S of the curl of f dot dr, well, ds rather. So here the S was the hemisphere. So ds, we know, and it's the unit hemisphere. It's rho equals to 1. Z greater than or equal to 0. So the surface area element here, this thing, if you will, is exactly sine phi d theta rho hat. Right? And the parameterization is what? We've written this a few times. Cosine theta, sine phi, sine theta, sine phi, cosine phi. That's the parameterization I need to think about. So I guess I'm working on the right-hand side to start with. Integral over S of the curl of f. dot ds. Now, what else can you tell me about this surface integral? What's the range of the parameters? I'll do the easy one. 0 less than or equal to theta, less than or equal to 2 pi. How about the phi? Pi over 2. Very good. So I'm supposed to do the integral from 0 to 2 pi, integral from 0 to pi over 2, and then the curl. Now, let's see here. I'll keep collecting things. What was the curl of f equal to? I think that was one of the things that you calculated right over here. So we've got, you're going to have to help me out. Minus 3z squared. What is it? E to the what? Z cubed? What's the second component?
Or z cosine of x.
Z cosine of xz, and then there's a second term there. Plus 2z e to the z squared or z cubed? It should be z cubed. It should be z cubed. That's like, if you got an e to the z cubed and you differentiated it, it never stops being e to the z cubed under differentiation, right? No? You know that.
There's an e to the z cubed in the first term. That might be where it came from.
Oh! You shouldn't back off your assertion. I forgot the e to the z squared up here. That can stay e to the z squared. You shouldn't. Don't accept my math bullying. So 2z e to the z squared. Right? Bullying's not cool. Let's see here. So I'll learn a lesson. All right. So oh, 2. It's harder for me to mess that up. There we go. All right. Now the thing is, we have to take. This is my x. This is the y. This is the z. You had to take those and shove them up in there to get the curl of f evaluated at the parameterization. Right? That's how we do the surface integral. We evaluate the vector field at the parameterization. And so what does that mean? So much suffering. Let's see here. Minus 3, cosine squared phi. I regret my life. E to the, no I don't. Let's see here. E to the cosine cubed phi. Why did I do this one? Cosine phi. I'm sorry, I'll stop cursing the problem soon. Cosine of, cosine theta, sine phi, gosh, cosine phi, comma. Oh, I still didn't get the other term, did I? Plus 2 cosine phi, e to the cosine squared phi. 2. And then I'm supposed to dot product with ds, right? Now that ds looks innocent enough, but the thing, you know, if I was to write ds out in gory detail, what is ds? Well, ds is want a decent red marker. The devil's in the details here, right? That rho hat, what does it mean? Rho hat is, well, it's exactly x, actually. This is funny enough. This is rho hat. Because we're on a unit sphere. So on a unit sphere, the parameterization and the unit vector normal to the parameterization are the same. So I think of this as being x. Well, this is rho hat, so equal. Anyway, the point is, if I multiply rho hat by sine phi, I get something still yucky, which is cosine theta, sine squared phi, comma, sine theta, sine squared phi, comma, sine phi cosine phi. And that's still all times what? Still times sine phi d phi d theta. So that goes down here. So, you know, it's kind of tough. Integral from 0 to 2 pi, integral from 0 to pi over 2. Let's take some dot products. We've got minus 3 cosine squared e to the cosine cubed phi times what? Times cosine theta sine cubed phi. Have I already multiplied the sine phi through? Yeah. Yay. Thank you. I welcome that question now as opposed to 2 minutes from now. If you guys could talk to my linear algebra class about proper question etiquette, it would be helpful for me. Sorry. Yeah, I make an error, and then like 3 minutes later, they're like, shouldn't that have been a... Like, ah! I'm already like half a board beyond it, you know? Anyway. There's one term. Oh, golly, cosine phi. I'll get my sine squared phi. And then I've got my sine theta, and then the ugly cosine of stuff. Oh, good grief, it's worse than that. It's worse than that. It's the wrong way to do it. We've got our sine theta, sine squared phi. Please be there. There must be a reason for this stuff to integrate to 0, most of it. And then cosine phi, cosine of this ugly stuff, cosine theta of sine, cosine theta, sine phi, cosine phi, plus 2 cosine, good grief, cosine phi e to the cosine, why did I do this? Cosine squared phi, why? And then plus finally, finally something decent, 2 sine phi, cosine phi. Let that be the only term that's non-trivial, please. Oh, and then d phi d theta. Phew, just in time. Almost ran out of board. All right. I am just itching for reasons to make these integrals go to 0. Aha. Yay. Look at this. So this guy is the only theta dependence of that first term. That's it. Right? And you're integrating from 0 to 2 pi in theta. That means 0. Whew. Well, that's a relief. Now, this times this. Look at that. The only theta dependence there is multiplication by sine theta. That term also integrates to 0 as we integrate over a full 2 pi. Thankfully, dead to us. This guy over here has no theta dependence whatsoever. That's going to survive. This right here I can't do my 2 theta trick on because you see I've got this cosine theta in here and the sine theta out here. So I'm actually going to have to face the music there. Oh, but that's not bad because it's actually a U substitution. We can do that. All right, let me do it. If you don't mind, I'm going to start with this term here, which gives me the integral 4 pi, the integral of, sine phi cosine phi d phi from 0 to pi over 2. So there's that. And then I also have to plus 0 to 2 pi. And let's see here. I'm going to have to make this a u. I think life is easier if I do the theta integration first. I think I should do the theta integration first. So I'm going to switch the order of bounds on this term to make life easier. 0 to pi over 2. And I'm going to, I'm going to do the theta integration first, but I'm going to change it to a u substitution. So if this is u, what's u when theta is equal to 0? What's u when theta is equal to 2 pi? Oh yeah. That's all right. It's sine phi cosine phi. It's sine phi cosine phi. I like that. I like that a lot. Now, what's du? I mean, I gotta make sure that the substitution actually makes sense. Du is sine phi. Ah, no. Well, maybe it's still okay. Sine theta d theta with a minus, yeah? All right, so we have the integral from, I'm going to call this stupid thing ghost. Integral from ghost to ghost. Integral from ghost to ghost. And we got ourselves a sine squared phi, right? Cosine phi, cosine of u, and then we got du over what? Minus sine phi cosine phi, right? Integral from ghost to ghost is 0. It was important for me to work that out to make sure the u substitution was legit. If I had done this and there had been a residual theta in the expression, then this u substitution wouldn't have been legitimate. And despite the fact that I invented this u and found the bounds were the same, it would be irrelevant, as it would not be a legitimate u substitution. But this is a legitimate u substitution, and it shows you that that theta integration, in fact, vanishes for arbitrary phi, which is all we need to ignore that term. Goodness, good night. So this, of course, is 4 pi, and this integrates to what? Like, what you got? You got like a sine squared phi over 2, evaluated from 0 to pi over 2, yeah? So 2 pi? Good news is, we just did the hard part of it. Now here's the easier part. The boundary of S is the unit circle on the equator, which has parameterization, r cosine t sine t 0, right? And so when we evaluate the vector field at r of t, we get 1 minus sine t, 1 plus cosine t, 1, plugging in x equals to x equals to cosine t, y equals to sine t, z equals to 0 into the formula for f. And so we just have to integrate. All we have to do then to calculate the integral around the boundary of S of f dot dr, well, that is the integral of 1 minus sine t, 1 plus cosine t, 1. What's my dr? Dr dt is minus sine t cosine t 0 dt. We want to go all the way around a circle. T should go from what? From 0 to 2 pi, right? And so that's the integral from 0 to 2 pi of what do we got? We've got ourselves a minus sine t plus sine squared t plus cosine t plus cosine squared t plus 0 dt, also known as the integral of dt from 0 to 2 pi, also known as 2 pi. Hey, what do you know? Stokes' theorem's true. Given the choice to verify half of Stokes' theorem, which half should you choose? Well, this example is misleading. There are other problems where, through some, crinkle of the example which is given, the flux of the curl is stupidly easy to calculate. It goes both ways, actually. But this is the connection. The curl's flux through the surface is equal to the line integral of the vector field being curled around the edge. This is a very non-obvious theorem. That's Stokes' theorem. That over there will have to wait for another day. Sorry. I can only work so fast. I tried. I seem not to have gotten to your task, John. I'm sorry.